Welcome to Academia. In our earlier class, we have already seen that a gradient of a scalar field produces a vector field, where gradient measures the maximum rate of change of that scalar field. For example, electric field is equal to gradient of potential, where potential is a scalar field. That is, maximum rate of change of potential occurs in the direction of electric field. As we know, this electric field is vector, so it is an example of a vector field. Now, what is the actual notion behind this vector field? In earlier class, we mapped points from region R, say P1 specified by x1, y1, P2 specified by x2, y2 into a different region fxy. Each point in the region fxy had different values of fxy, but no direction was associated with them. That is why it was called a scalar field. Now, if each point within fxy has distinct values as well as different directions associated, then fxy is said to be vector field. So, in this vector field, q1 has a value fx1, y1 and a direction, while q2 had a different value fx2, y2 and a different direction. Now both the value and direction change from q1 to q2 in this vector field. How fast this change is happening? What is the nature of this change? That is complicated here, since both the change in value and change in direction have to be considered together. We use two different measures to find the rate of change of vector field. One is divergence of vector field, another is curl of vector field. Today we shall study divergence of vector field. Before starting this, we need to know what necessitated the concepts of this divergence or curl. Actually, they were invented to study fluid dynamics. Let's take water pipe for example. Water is flowing through this pipe. Pipe has an inlet where water enters and an outlet where it exits. Now water is entering the pipe at a specific rate. That rate of flow is actually velocity. Now if the value of velocity and the direction of velocity is different at different points within this pipe, then it can be considered as a vector field. So it is a velocity vector field within the pipe. If the rate of inflow is not equal to rate of outflow, then that means there's a change in this vector field. That means the value of velocity vector diverges from its original value. How much does it diverge? That is measured by divergence. It is basically the difference between the outflow rate and the inflow rate. Outflow rate is measured by total outflow by volume. Similarly, inflow rate is measured by total inflow by volume. Let's take a differential volume dV in 3D Cartesian coordinate system with sides of length dx, dy and dz. Let electric field D is a vector that flows through it. It's basically flux density. Now this D vector has three components: dx along x direction, dy along y direction and dz along z direction. So D equals to dxi plus dyj plus dzk. Let us consider that dy component first. Dy enters from left and leaves the volume in right. From Gauss's law we know the closed surface integration of d over the surface is equal to phi, which is electric flux. ds is the area through which the flux passes. dy enters through this rectangular area of sides dx and dz, so the area is dx dz. So total inflow of the flux is d dot area equals to dy dx dz through this surface. Say dy changes from y equal to 0 to y equal to dy. So the change in dy along y direction is dy is equal to rate of change of d along y direction into dy. So total outflow of flux through the area of same value dx dz is dy plus dy whole into dx dz. So total change in dy through this volume equals to outflow minus inflow. It is not outflow rate and inflow rate, it is outflow minus inflow, which is equal to dy plus dy whole into dx dz minus dy dx dz, which gives dy dx dz. Now we have already obtained the expression for dy, which is del y of dy into dy. Similarly, change in dx along x through this volume will be del x dx into dx dy dz, and that along z direction for Ez will be del z dz into dx dy dz. So total change in d through this volume will be equal to the summation of all these three. That means taking dx dy dz common from this part, so within the bracket it comes as del x ex plus del y ey plus del z ez into dx dy dz. Dx dy dz is the volume of this cube, that is through which the flux passes. So the total change in E per unit volume will be divergence of D, since change in rate of flow is measured per unit volume. Now this expression can also be written as del x I cap plus del y j cap plus del z k cap dot dx I cap plus dy j cap plus dz k cap. We know this is del and this is d vector, so it is equal to del dot d. Since dot product between two vectors is scalar, so divergence of d evidently is a scalar quantity. So divergence is basically change between inflow and outflow rate, which is given by outflow rate minus inflow rate. Now this change can either be positive or negative. When outflow rate is greater than inflow rate, the divergence is positive. Now how does flux coming out of this volume be more than what was entering? How come less water is going in and more water is coming out? There must be some source of flux or water inside this pipe, which is adding to the quantity that enters the pipe. If water or flux coming out of the pipe is less than what was entering, then some amount of water or flux is getting absorbed within this pipe. That means there must be some sink within it, which absorbs or reduces the water or flux entering the pipe. So divergence basically measures the net rate of change of flux through it. So it can be written as del phi by del v. So the divergence basically measures the rate of change of flux with respect to volume when the volume is differential volume, that is infinitesimally small volume. So it can be written as del phi by del v when del v tends to 0. From Gauss's law, we know the closed surface integration of d dot ds gives us phi. So if d passes through a small surface del s instead of s, then it should give del phi. So in place of del phi we can write, so if there is no source or sink within this pipe, then the closed integration of E dot ds over the small surface del s has to be 0. Then divergence of E will be equal to 0 if there is source. Then this integration will have a positive value. So divergence of E will be positive. If there is sink, then this closed integration of E dot ds will have a negative value. Then divergence of D will be negative. Now this can be written as d phi dv by the definition of derivative. Del dot d equals to d phi dv. Now in place of phi, from Gauss's law we can write closed integration of E dot ds over the surface S. Now if we integrate on both sides with respect to volume, then we have volume integration of del dot d equals to closed surface integration of d dot ds over the surface S. This is the mathematical expression for divergence theorem. In our next class, we shall study the curl of a vector field. Don't forget to leave your feedback in the comments below and tell us how do you like our classes. So if you wish to attend our offline classes, you are most welcome to visit our tutorial home at New Goria near Kavi Subhash metro station. So the students of West Bengal University of Technology, popularly known as WBUT, can subscribe to the YouTube channel of Pandora's Reel and can avail all the classes for free.